Welcome to Module 1, the Mindset Shift. In this module, we're going to explore something that fundamentally changes how you think about building and working with AI products, the shift from certainty to probability. Traditional software systems are deterministic. You give them the same input, you get the same output, every time, without fail. That predictability is the foundation of how we've built, tested, and trusted software for decades. But AI products work differently. They are probabilistic by nature, meaning the same input can produce varied outputs, and that's not a bug. That's by design. This isn't just a technical detail, it's a mindset shift, one that affects how product teams plan, how QA teams test, and how leaders make decisions. Over the next slides, we'll unpack exactly what this means, and why embracing this shift is essential to building intelligent systems that actually work in the real world. So why does this topic matter? Because AI is no longer confined to tech companies. It's everywhere. Healthcare teams are using AI for diagnostics and triage. Financial institutions are deploying it for fraud detection and risk assessment. Retailers are leveraging it for personalized recommendations. And tech teams are building coding assistants and autonomous agents. Universal adoption is already here. But here's the problem. Most teams are walking into AI product development with a traditional software mindset, and that creates a dangerous expectation mismatch. They expect deterministic behavior. AI delivers probabilities. When that gap isn't understood, it becomes a risk of failure, not because the AI is broken, but because the people building around it didn't understand its nature. That's why a new mindset is needed, one that shifts the focus from simply building features to actively managing uncertainty. Understanding the why behind this shift, that's where success begins. Let's get to the heart of it, the core shift between traditional systems and AI systems. In a traditional system, the output nature is entirely predictable. Given input A, the system will always produce output B based on fixed, pre-written rules. There's no ambiguity. The key question a traditional system answers is, what will happen? And you know the answer before it runs. Now contrast that with an AI system. The output nature here is probabilistic. Given input A, the system produces the most probable output B, but it's not guaranteed. Run it again, and you might get something slightly different. The key question an AI system answers is, what is likely to happen? And that's a fundamentally different framing. This isn't a weakness. It's the very reason AI can handle complexity, nuance, and ambiguity that rule-based systems never could. But it does require a shift in how we think, build, and measure success. Let me make this tangible with an analogy you already understand. Think about a calculator. It's deterministic. You type in 2 plus 2, and it gives you 4. Every single time. No surprises. That's rigid logic, and it's always correct within its rules. Now think about a weather forecast. It's probabilistic. The meteorologist doesn't tell you it will rain. They tell you there's a 60% chance of rain. That forecast is built on pattern recognition, vast amounts of historical data, giving you the most likely outcome. But it might rain anyway, or it might not. Here's the aha moment. Most teams approach A. I like a calculator that broke. Frustrated when it doesn't give the same answer twice. But AI was never a calculator. It's always been a weather forecast. Helpful, intelligent, pattern-driven, but not perfect. And that's okay. The shift is in your expectations, not in the technology. This isn't just a technical conversation. It directly affects your business outcomes. When teams fail to adapt to the probabilistic nature of AI, 3 costly problems emerge. First, expectations misalignment. Stakeholders conditioned by traditional software expect perfection. When AI outputs vary, they reject them. Projects stall. Resources are wasted chasing 100% accuracy, a standard that was never realistic to begin with. Second, trust erosion. Unlike a traditional bug, which is clearly a system error, an AI hallucination can feel like the system is lying. Without proper framing up front, a single bad output can destroy user trust entirely. And rebuilding that trust is expensive. Third, risk-based decisions. Leadership must evolve from binary go-no-go thinking to genuine risk management. That means defining acceptable failure rates, not demanding perfection. And that brings us to the key insight of this entire module. Success with AI doesn't come from eliminating uncertainty. It comes from managing it. Now that we understand why this mindset shift matters, let's map out exactly where we're going in this session. We have 4 stops on this journey. We start with deterministic systems, the world most of us come from. Rules, logic, and certainty. The foundation of traditional software that has shaped how we think about building products for decades. From there, we move to AI nature, unpacking what it really means for a system to be probabilistic. We'll explore probability, likelihood, and non-determinism in a way that's practical and grounded. Our third stop is key differences, where we place both worlds side by side. Development approaches, testing strategies, and risk profiles, compared directly so the contrast is crystal clear. And finally, we arrive at implications, the part that ties it all together. product strategy, governance, and managing expectations, in a world where AI is at the core. 4 stops. 1 powerful shift. Let's go. Welcome to Module 2, where we take a deeper look at deterministic systems, the foundation most of us were trained on. By definition, a deterministic system is one in which no randomness is involved in the development of future states. Every output is fully determined by its input and the rules applied to it. Put simply, same input equals same output. Always. Look at the flow on screen. Input A enters a logic engine of fixed rules, and out comes output B, a guaranteed result. It's captured beautifully in the equation, f of x equals y. No ambiguity, no variation. 2 properties define this approach. First, predictable consistency. Run the system 1,000 times, you get 1,000 identical results. Second, rule-based logic. The system operates on explicit if-then-else instructions, written and controlled entirely by humans. This is the world of traditional software. Reliable, traceable, and exact, but limited in its ability to handle complexity. Let's look under the hood of traditional software, because understanding it deeply is what makes the AI contrast so powerful. Traditional software runs entirely on explicit programming. Nothing happens by magic. Every action, every decision, every output is the direct result of a human-written line of code. Look at the example on screen. A simple bank transfer function. If the balance is greater than or equal to the amount, the transaction is approved. If not, it's rejected. That's it. Clean, traceable, binary. This is if-else logic at its core, decision trees that define every possible path. If the user clicks the button, then save the file, else show an error. Every branch is anticipated and coded in advance. And that leads to the third characteristic, fixed workflows. The system cannot improvise. If a scenario hasn't been coded, the system either fails or throws an exception. Powerful within its boundaries, but completely unable to handle what it wasn't explicitly taught. Let's make deterministic systems concrete with 3 real-world examples. Industries where absolute precision isn't optional, it's mandatory. Take banking transactions. A transfer of $100 cannot be probably $100. Financial ledgers must balance to the cent every single time. The logic is unambiguous. If funds are sufficient, transfer. No gray area, no approximation. Now consider payroll processing. Employees expect their paycheck to be calculated exactly right, not approximately right. Tax formulas follow strict government rules. Net pay equals gross minus deductions. The formula never changes based on context or mood. And finally, inventory systems. Stock counts are integers. You cannot have 0.7 of a laptop in a warehouse. Logic dictates reorder points precisely. If stock drops below 10, reorder. Simple, traceable, exact. What all 3 share is this: they require absolute precision, full auditability, and zero ambiguity. These are the domains where deterministic systems are not just preferred, they're essential. So why do we still build rule-based software? Because in many scenarios, certainty isn't just preferred, it's required. Let's look at the 4 core strengths that make deterministic systems irreplaceable. First, reliability. The system performs consistently under identical conditions. It doesn't get tired, doesn't have bad days, and absolutely does not hallucinate. You can bank on it, literally. Second, testability. Testing is beautifully binary, pass or fail. You can write unit tests for every edge case and know with complete certainty whether the code works as intended before it ever reaches production. Third, auditability. Every single decision can be traced back to a specific line of code. When something goes wrong, you can pinpoint exactly which logic path caused it, crucial for debugging and accountability. And fourth, compliance friendliness. Regulated industries, healthcare, finance, require explainable, transparent decisions. Deterministic systems satisfy those legal requirements naturally. These strengths explain why deterministic thinking runs so deep, and why unlearning it takes deliberate effort. We've seen the strengths. Now let's be honest about where deterministic systems hit a wall. Because while they're reliable, they struggle badly when faced with the messy, unpredictable nature of the real world. This is what we call the brittle trap. Traditional software doesn't bend when it encounters something unexpected. It breaks. If a scenario isn't coded, the system crashes. Full stop. 3 limitations drive this brittleness. First, they cannot handle ambiguity. If inputs aren't perfectly structured and clean, the system fails. It cannot guess, approximate, or figure things out from context. Input maybe, and you get an error. Second, they're hard to scale in complexity. As rules multiply, they start to conflict. Managing 10,000 if-else statements becomes a maintenance nightmare that actively slows down development. Third, everything requires manual rule creation. Every scenario must be anticipated by a human. If you didn't think of it, the software can't handle it. Innovation is permanently limited by human foresight. And that's exactly the gap AI was built to fill. One of the greatest advantages of deterministic systems is how cleanly they can be tested. In this world, testing is binary, pass or fail. We know exactly what the answer should be, so we can prove correctness with 100% certainty. The test coverage target? 100%. No ambiguity allowed. The automated test suite runs 3 layers of validation. First, unit testing, isolating individual functions to verify they return the correct output for every known input. Each function, tested in isolation, proven correct. Second, integration testing, verifying that different modules interact with each other exactly as defined in the interface specifications. No surprises at the seams. Third, expected output validation, comparing actual results against a hard-coded truth file. Any deviation at all is treated as a failure. The result? 452 tests passed, 0 failures. Total runtime, 0.45 seconds. All logic verified. This is the gold standard of traditional QA, and it's what makes the shift to probabilistic testing so challenging for teams to accept. Welcome to Module 3, where we shift from the world of certainty into the world of likelihoods. Unlike deterministic systems that follow a single fixed path, probabilistic systems deal in probabilities. They don't output the answer, they output the most likely answer. Look at the probability distribution curve on screen. This is what an AI system actually sees when generating a response. At the peak, the most likely output, with an 85% probability. To the left, a valid alternative response, at 10%. And at the tail, an edge case, just 5%. 2 properties define this behavior. First, likelihood-based outputs, generated not from fixed rules, but from statistical probability distributions trained on vast amounts of data. Second, non-determinism. The same input can produce slightly different outputs depending on the model's state at that moment. This isn't a flaw in the system. It's the architecture that allows AI to handle nuance, context, and complexity that no rule-based system ever could. So if AI doesn't run on handwritten rules, how does it actually work? The answer: instead of explicit programming, AI systems build their own logic through exposure to massive amounts of data. It happens in 3 stages. Stage 1, learn patterns. The system ingests vast datasets, text, images, numbers, and identifies hidden correlations and structures that humans might never notice on their own. This is raw data ingestion at scale. Stage 2, statistical models. From that data, the system builds a multi-dimensional statistical model, a network of weights and biases that represent the relationships between data points. This is the training and tuning phase, where the intelligence is actually shaped. Stage 3, generate output. When you query the model, it doesn't retrieve a pre-stored answer from a database. It generates the most statistically probable response, based on everything it learned during training. The output is the highest probability token, the most likely next step. No rules written by humans, just patterns learned from data. Let's bring this to life with 4 AI products you likely interact with or build every day. Each one navigates ambiguity to deliver likely, context-aware outcomes rather than rigid answers. Chatbots and LLMs, like the one powering this very coaching series, generate human-like text by predicting the next most likely word. Responses vary based on context and creativity settings. Output: varied text. Recommender systems. Think Netflix or Spotify. They predict your preferences based on patterns. A movie recommended today might shift tomorrow as new user data comes in. Output: a ranked list. Fraud detection. Rather than following a simple rulebook, these systems analyze behavioral patterns and assign a risk score probability to every transaction. Output: a risk percentage. And computer vision, it doesn't know it's a cat. It's 98.5% confident the pixel pattern matches a cat. Output: a confidence score. Notice the pattern. Every single AI output is a probability, not a certainty. That's the signature of probabilistic systems in the real world. Now let's crystallize the 3 defining characteristics that make AI systems fundamentally different from everything we've built before. First, non-deterministic. The same input doesn't always guarantee the same output. Results vary based on probability, temperature settings, and the model's current state. This isn't inconsistency. It's the system operating exactly as designed, sampling from a distribution of likely answers each time. Second, context-sensitive. AI doesn't process inputs in isolation. Meaning is derived from surrounding information, conversation history, prompt structure, prior context. The system continuously adapts its understanding based on everything around the query. Ask the same question in 2 different conversations, and the context shapes 2 different responses. Third, data dependent. An AI system's performance relies entirely on the patterns found in its training data. And this is critical. Limitations and biases in the data become limitations and biases in the product. The model is only as good as what it learned from. These 3 characteristics define how AI thinks, and how we must think about AI. A question worth asking: why is AI probabilistic in the first place? Is it a limitation or a deliberate design choice? The answer is both, and understanding why makes everything else click. 3 fundamental reasons. First, real-world ambiguity. The world simply isn't black and white. Language is messy. Human intent is fuzzy. Images are noisy. A deterministic system would crash, trying to process the sheer ambiguity of real human input. AI must make its best guess about the most likely meaning, and that requires probabilistic thinking. Second, incomplete data. Models never have perfect information. There will always be gaps. So like a skilled human expert drawing on intuition and experience, AI fills those gaps using statistical patterns learned during training. It reasons under uncertainty, and does it remarkably well. Third, human-like reasoning. We don't actually want rigid logic from our AI. We want nuance, creativity, adaptability. Probabilistic systems mimic how the human brain weighs evidence to reach conclusions, allowing AI to be genuinely useful in complex, real-world situations. Probabilistic isn't a bug, it's the blueprint. Let's make non-determinism visceral with a live demonstration. 1 prompt, submitted 3 times, 3 completely different outputs. The user input is identical every time. Write a short poem about the ocean. Attempt 1, standard settings. The poem is titled, The Blue Expanse. Gentle, rhythmic, visual. Waves crashing on golden sand. Attempt 2, creative temperature set to 0.9. Now we get midnight depths, darker, more mysterious. The mood has shifted entirely. Same prompt, completely different emotional register. Attempt 3, with added context. The result is, The Sailor's Home. Personal, reflective, narrative. The surrounding context has pulled the output in a new direction altogether. 3 attempts. Same input. 3 valid, yet distinct, responses. And here's the key takeaway at the bottom of the slide. Unlike a calculator where 2 plus 2 always equals 4, AI outputs depend on probability, temperature settings, and context. This is non-determinism in action, not a malfunction, a feature. This slide introduces one of the most important concepts for anyone building or evaluating AI products, the difference between accuracy and confidence. In traditional software, correctness is binary, pass or fail, 1 or 0. But AI outputs exist on a spectrum. An answer can be mostly right, or plausible but inaccurate. That makes strict pass/fail validation genuinely challenging. Look at the confidence gauge, 78%, sitting just above the threshold of 0.75. The model is reasonably confident, but not certain. And that threshold is a product decision, not a technical one. Confidence scores matter. A score of 0.98 signals high certainty. A score of 0.45 means the model is essentially guessing. Smart products surface this distinction, and this creates trade-off decisions for product managers. Do you show a low-confidence answer and risk being wrong, optimizing for recall? Or suppress it and risk missing a valid answer, optimizing for precision? High-stakes context demands a high threshold. Creative applications can afford a lower one. These are judgment calls that define product quality. Because AI deals in probabilities, it can make confident mistakes. And that combination, confidence plus incorrectness, is what makes AI failures uniquely dangerous. Understanding these failure modes is essential for building trustworthy products. There are 3 critical failure modes every product team must know. Hallucinations, a factuality risk. Models may confidently invent facts, citations, or code that simply doesn't exist. Why? Because they prioritize fluency and pattern completion over factual accuracy. The output sounds right. It just isn't. Bias, a fairness risk. If the training data contains societal stereotypes or skewed distributions, the model doesn't just reproduce those biases, it amplifies them in its outputs. Garbage in, amplified garbage out. Drift over time, a reliability risk. A model trained on 2023 data may quietly degrade by 2025 as language evolves, trends shift, and user behaviors change. Static models in a dynamic world become unreliable without continuous monitoring. Knowing these failure modes isn't pessimism, it's the foundation of responsible AI product design. Welcome to Module 4, where we place both worlds directly side by side so the contrast is impossible to miss. Let's walk through 3 dimensions of comparison. Logic source. Deterministic systems run on fixed rules, explicit if this then that, programming logic written entirely by humans. Probabilistic AI systems run on learned patterns, statistical associations derived from training data. One is authored, the other is discovered. Output nature. Deterministic systems are fully predictable. The same input always yields the exact same output, without exception. Probabilistic systems are variable. Outputs can change based on context, randomness, or temperature. Same prompt, different response. Result type. Deterministic systems produce exact results, binary outcomes. Pass or fail. True or false. No gray area. Probabilistic systems produce likely results, confidence intervals, and probability distributions. Not the answer, but the most probable answer. 3 rows, 3 fundamental differences. And together they explain why building, testing, and trusting AI requires an entirely different playbook from traditional software. The difference between these two paradigms isn't just in how they behave, it's in how they're built. And this slide captures that beautifully with 2 roles: the architect versus the teacher. In traditional software development, the engineer is the architect. The process is define rules, write code, compile and deploy. Business logic is explicitly mapped out. If user clicks X, then do Y. Developers write those instructions in C++, Python, or Java. Once compiled, the logic is frozen. It will behave exactly as written until someone manually updates it. In AI systems development, the engineer is the teacher. The process is entirely different. Curate data, train the model, fine-tune and evaluate. Instead of writing rules, you gather thousands of examples, inputs paired with desired outputs. The system processes that data to learn the statistical relationships. Then you adjust hyperparameters and retrain until performance reaches an acceptable level. Same goal, build something that works. Completely different paths to get there. If there's one operational area where the deterministic to probabilistic shift hits hardest, it's testing. The entire methodology has to change. In traditional testing, the model is simple: pass or fail. Output must exactly match the expected result. Tests are binary: 100% pass or 0% fail. And regression suites ensure new code never breaks old rules. Clean, absolute, unambiguous. AI evaluation looks completely different. Look at the dashboard on the right: 94.2% accuracy score. Precision at 0.89. Recall at 0.92. These aren't pass/fail results. They're statistical metrics, measured in aggregate across thousands of test cases using scores like F1. 3 new practices define AI testing. Statistical metrics replace exact match requirements. Threshold tuning replaces binary acceptance. Teams actively adjust where to draw the line between acceptable and unacceptable based on trade-offs. And dataset splits, training, validation, and test sets replace simple regression suites. The question shifts from "did it pass?" to "is it performing well enough across the distribution?" A fundamentally different standard of quality. Look at the 2 containers on this slide. One is nearly empty. The other is completely full. That visual tells the entire story of data dependency. In traditional systems, data is minimal. It's primarily a record of past transactions. The system's logic lives in the code, not the data. Critically, the system functions perfectly, even with an empty database. You could wipe all the records, and the software would still know exactly what to do. Data is a passenger, not the driver. In AI systems, data is the critical fuel. It's not a record, it's the source of intelligence itself. The system literally learns its logic from the data. There is no logic without it. Without massive, high-quality datasets, the product simply cannot function. This changes everything about AI product strategy. Data collection, data quality, data governance, these aren't infrastructure concerns. They are core product concerns. If your data pipeline is broken, your AI product is broken. Full tank or empty tank, the difference is everything. This slide tackles one of the most consequential differences between the 2 paradigms: explainability. And the visual says it all: a transparent box versus an opaque one. Traditional systems are a white box, fully explainable, high transparency. Every output can be traced back to a specific rule or line of code. If something goes wrong, you can pinpoint exactly why in the logic flow. Audit trails are absolute. Debugging is deterministic. Regulators, lawyers, and customers can all be shown exactly how a decision was made. AI systems, particularly deep learning models, are often a black box, opaque, low transparency. These models make decisions across billions of parameters. It is frequently impossible to explain precisely why a specific output was generated. The reasoning is emergent. It arises from the model rather than being written by a human. The why is itself a probability distribution. This creates real challenges in regulated industries, legal accountability, and user trust. And it's why explainable AI, making AI decisions interpretable, has become one of the most critical fields in responsible product development. Look at the risk spectrum across the top of this slide. Traditional software sits firmly in the safe, low-risk zone. AI systems sit at the critical, high-risk end. That gap demands serious attention. Traditional software carries low uncertainty. It's a controlled environment. Risk is primarily associated with logic errors or bugs in the code. If the code is correct, the output is guaranteed to be correct. Failure modes are predictable. Bugs and crashes. Errors are reproducible and auditable. Compliance is straightforward to verify. AI systems carry high uncertainty, a probabilistic environment. And here's the unsettling truth. Risk is inherent in the model's statistical nature. Even a perfect model can produce incorrect or biased results unexpectedly. 3 warnings define this profile. Unpredictable failures including hallucinations, silent drift over time as underlying data changes, and black box decision-making that actively complicates audits. This doesn't mean AI is too risky to deploy. It means risk management must be built into the product strategy from day one, not treated as an afterthought. The probabilistic shift doesn't just affect how we build, it fundamentally changes how users experience and feel about the product. This slide captures that emotional dimension beautifully. With traditional software, the relationship is transactional guaranteed outcomes. The user clicks calculate, the system executes a fixed formula, and the result is 100% correct. The user's expectation is certainty, and critically, if the result is ever wrong, the user feels frustrated, betrayed even, because the contract was perfection. With AI systems, the relationship is collaborative, probabilistic outcomes. The user says, suggest a plan. The model predicts the most likely tokens and responds with, here are 3 options, approximately 85% likely to be relevant. The user's expectation is assistance, not perfection. And this is where product design becomes crucial. When users understand they're collaborating with an AI, curating and editing its suggestions, they feel empowered, not disappointed. The mindset shift isn't just for builders, it's for users too, and you are responsible for setting that expectation through your product. Deploying AI without governance isn't bold, it's reckless. And this slide makes clear that AI demands a fundamentally stronger oversight framework than anything traditional software required. Stronger governance is required. In deterministic systems, code is law. Behavior is explicit and bounded. In AI, behavior is emergent. You cannot fully predict what a model will do in every situation. That's why organizations need strict frameworks covering ethics, bias mitigation, and safety boundaries before a single user touches the product. Continuous monitoring is non-negotiable. You simply cannot set and forget an AI system. Once deployed, it must be monitored in real time, watching for model drift, hallucination spikes, and data quality degradation. The model that worked perfectly in January may silently degrade by June. Essential controls must be built in. This means implementing kill switches and human-in-the-loop workflows. When confidence scores drop below a defined threshold, the system should automatically defer to a human expert, not guess its way through a high-stakes decision. Active oversight isn't overhead, it's the product. The shape of these 2 diagrams tells the whole story, a triangle versus a circle. And that geometric difference represents a profound operational reality. The traditional software lifecycle is a triangle, a linear progression. Build the logic, deploy the binary, maintain by fixing bugs. The logic is static between releases. You ship it, it runs, you patch it when it breaks. Predictable, sequential, finite. The AI lifecycle is a circle, a continuous feedback loop with no natural endpoint. It starts with training the model to learn data, then validation to check accuracy, then monitoring in production to detect drift. And when drift is detected, which it will be, you retrain with updated data, then validate again, then monitor again, forever. Why? Because the world changes, language evolves, user behavior shifts, data distributions move. A model that was accurate at launch will degrade silently over time and must be retrained to stay relevant. This circular loop isn't a burden. It's the ongoing investment required to keep an AI product genuinely valuable. We've covered a lot of ground across these 4 modules. And now we arrive at the single most important idea to carry forward, the one insight that ties everything together. AI is not better software. That framing, however intuitive it feels, is the root cause of most AI product failures. It leads teams to apply the wrong mental models, the wrong testing approaches, the wrong governance frameworks, and the wrong success metrics. AI is not a faster calculator. It is not a smarter database. It is not an upgraded if-else engine. It is a fundamentally different paradigm. The shift, captured at the bottom of this slide, is elegant in its simplicity, from coding rules to training behaviors. You are no longer an architect writing instructions. You are a teacher shaping how a system learns to think. That shift changes everything. How you build, how you test, how you govern, how you set expectations, how you measure success. Embrace the paradigm, and everything else becomes clearer. Welcome to Module 5, where understanding transforms into action. Knowing AI is probabilistic is step 1. Building products that embrace it is what separates great AI teams from struggling ones. The new product mindset rests on 3 pillars. First, accept uncertainty. Stop trying to force deterministic outcomes from a probabilistic system. That battle cannot be won. Instead, embrace confidence intervals and probabilistic ranges as a core feature of your product, not a bug to be apologized for. Uncertainty, communicated well, builds trust. Second, design for variability. Your interfaces must be adaptive. Build for the reality that outputs will vary. Use suggestions, drafts, and regenerate options to give users agency in managing that variety. The UI should expect multiple valid outputs, not break when they appear. Third, build feedback loops. The product is never done at launch. Design explicit mechanisms for user correction: thumbs up, thumbs down, edits, flags. Every correction is data. Every data point retrains the model. Every improvement compounds. Build for the loop, not just the launch. Great AI products aren't just technically sound, they're designed to work with probabilistic outputs. This slide shows exactly what that looks like in practice. Look at the AI assistant interface. A user asks for a tagline for their eco-friendly coffee shop. The response comes back, but notice what's shown alongside it. Confidence, high 87%. That's intentional design. Don't imply certainty where there isn't any. Visually signal the model's probability score so users can calibrate their trust accordingly. Below the primary response are edit, regenerate, copy, thumbs up, and thumbs down controls. This is allowing user correction by design. The user is always the final editor. Every regenerate click, every thumbs down, that's feedback that makes the model smarter over time. And critically, 2 alternatives are offered immediately. Provide fallbacks. If the first answer isn't right, don't make the user start over. Surface variations instantly. Nature's brew in every drop. Green beans, clean dreams. 1 prompt. 1 primary answer. 2 alternatives. Full user control. This is what designing for variability actually looks like. When building AI products, what you measure defines what you manage. This slide breaks down the 4 metrics that truly matter. First, accuracy. Our model hits 94.2%. That's a 5.2% jump over the 89% baseline. It tells us how often the model gets it right overall. But accuracy alone isn't enough. That's where precision and recall come in. Precision asks, when the model flags something, how often is it correct? Recall asks, how many real cases did it actually catch? Across models A, B, and C, we're balancing both, because getting this trade-off wrong has real consequences. Third, user trust. With a CSAT score of 4.8 out of 5, users find this product transparent and helpful. In AI, trust isn't a soft metric, it's a survival metric. And finally, business impact. From Q1 to Q4, the value delivered, whether time saved or revenue generated, has grown consistently. That's the ultimate proof point. Technical performance plus human trust, plus business value. That's the full picture of an AI product that works. An AI product is never truly finished, and that's by design. Slide 34 introduces us to continuous learning systems, built on one core truth. The AI product lifecycle is circular, not linear. It starts with monitor performance, continuously tracking model accuracy, latency, and user feedback in production. Because real-world conditions change, and your model needs to keep up. When those conditions shift, step 2 kicks in: detect and handle drift. This is when real-world data starts diverging from the patterns the model was trained on. Catching drift early is what separates resilient AI products from ones that silently fail. That detection triggers step 3, retrain and deploy. Fresh data goes in, the model gets updated, and performance and relevance are restored. Then the cycle begins again. Monitor, detect, retrain. This infinite loop is what keeps AI products sharp, trustworthy, and aligned with the world as it actually is, not just as it was when training ended. Building a powerful AI product is only half the job. The other half is making sure it operates responsibly. Slide 35 introduces the responsible AI framework, built on 3 pillars. First, human in the loop. Critical decisions can't be left entirely to the machine. Low-confidence predictions get reviewed before action is taken. High-stakes domains like finance and health require mandatory human approval. And there's always a feedback mechanism to catch and correct model errors before they compound. Second, bias checks. Fairness isn't assumed. It's tested. Models are evaluated against diverse datasets before launch, monitored for disparate impact on protected groups, and audited regularly by third parties. Because a model that works for some users but not others isn't a success, it's a liability. Third, audit trails. Every input, output, and decision logic is logged. Model versions and training data lineage are tracked, and immutable logs are maintained for regulatory compliance. If something goes wrong, you need to be able to explain exactly what happened and why. Governance isn't a constraint on AI innovation. It's what makes that innovation sustainable and trustworthy. Congratulations, you've unlocked the probabilistic mindset. Let's close Module 5 with 3 takeaways that should change how you think about AI products forever. Takeaway 1. AI is not better software. It's not an upgrade to traditional code. It's a fundamentally different paradigm, one that demands new development life cycles, new testing methods, and an entirely new mental model from everyone building with it. Takeaway 2. Probability is core. Uncertainty in AI is not a flaw to be fixed. It's a feature to be managed. Confidence scores and variability aren't warning signs. They are the output. Embrace them as the new standard, And takeaway 3, we must adapt. Product teams, business leaders, and governance functions all need to make the same shift, from expecting guarantees to managing risk and trust. That's the operating reality of AI. These 3 ideas sit at the heart of everything covered in this module. Carry them forward, because the teams that internalize this mindset are the ones who will build AI products that are not just powerful, but responsible, resilient, and ready for the real world. We've covered the frameworks, the metrics, and the mindset. Now it's time to turn the lens on your own organization. Slide 37 opens the floor with 2 critical questions. Question 1. Where can AI fail in your organization? Think about the high-risk processes in your day-to-day operations. Where would a probabilistic error, a wrong prediction, a biased output, a drifted model cause the most damage? Finance approvals? Patient triage? Customer-facing decisions? Identifying those pressure points now is far better than discovering them in production. Question 2. What assumptions need to change? Your product roadmap was likely built around deterministic systems, software that does exactly what it's told. AI doesn't work that way. So how must your testing strategies evolve? How should user expectations be reset? What does your team need to unlearn before it can truly build with AI? This isn't just a theoretical exercise. Product, execs, engineering, design. Every function in your team has a stake in these answers. So take a moment, discuss. Because the organizations that ask these hard questions early are the ones that build AI products that last.